Let's now take a look at other functions defined in the complex plane. Let's have a look at trigonometric functions and hyperbolic functions. Turns out these are intimately related once we move over to complex numbers. Where do we begin? Let's begin with Euler's formula. And let's also consider the conjugate of this. So I take conjugate of that of Euler's equation, I get this. Then if I add and subtract these equations, I can get unique formulas for sine theta and cos theta. So the relationship then between the exponential function and the sine and cosine functions becomes clear now that we have these two formulae. So these are defined for theta being a real number, but we can just go ahead and extend this to the complex numbers by just asserting that these are the definitions of the sine and cosine functions throughout the complex plane. So what I'll do is just say that this is true for all z in C. So these give good definitions of sine and cosine, which are valid throughout the complex plane, and reduce to the normal sine and cosine functions when I move to the real axis. Now a cool thing happens if I consider cos of I times z. What does this become? Well, using these definitions, then I have e to the minus z plus e to the plus z. And this is none other than the cosh function. So cosh is actually cosine of I times z. Similarly, it's not quite so simple, but this is equal to I times sinh. So if we try and visualize what cos looks like in the complex plane, then along the real axis, it's just oscillating like the normal cos function. Elsewhere in the complex plane, it's a complex number, so it's not so easy to analyze. Along the imaginary axis, it becomes real again, and it's the cosh function, so it's growing in both directions. So it's quite difficult to imagine complex functions of complex variables. One can do it with careful colouring and so on. But one thing to note is that cos z is no longer bound between -1 and 1, and so the modulus of it can actually be larger than 1. And of course along the imaginary axis, that's now going to be the case, moving away from anywhere away from the origin. In fact, let's try an example. Let's look for solutions for when sine z is equal to 3. Now this is something which has no solutions in just considering the real numbers, but in the space of complex numbers, we'll see there are infinitely many solutions to this. How do we go about finding z? Well, let's use a definition. Substituting for sine z, multiplying through by 2i gives me this equation e to the iz minus e to the minus iz equals 6i. Now let's let w equal e to the iz, which means that this equation is actually a quadratic in w. And I can just go ahead and solve this quadratic, and this is equal to e to the iz. So I found e to the iz is equal to two distinct roots, 3 plus or minus 2 root 2 times I. So I can write this in modulus argument form, and then it's a simple case of trying to get z out of this. And what I do is I let z equal x plus iy, and then what I've got is the formula. Now it's just a question of equating moduli and arguments on both sides. So y is equal to minus the log of 3 plus or minus 2 root 2, and I note that 2 root 2 is less than 3, so this number is positive for both of these values, and x is pi by 2 plus 2n pi. And therefore, the solutions which satisfy sine z equals 3, z equals pi by 2, plus 2n pi for the real part minus the logarithm of 3 plus or minus 2 root 2. And in fact I can write this as pi by 2 plus 2n pi plus or minus I times log 3 plus 2 root 2. That's not a particularly trivial step, so you have to fiddle about with the number inside the log to show this. So now we've got this, we can then plot the solutions. So let's start with the first one when the real part is pi by 2, the imaginary part is plus log 3 2 root 2, so let's stick that there. So this distance, a series of solutions spaced 2 pi apart. And there's another set of solutions for the negative value, which are just a reflection in the real line. And this is then the set of all solutions of sine z equals 3. We can actually do some neat tricks using this definition of sine and cosine. Let's try the integral e to the x cos x dx. Now we saw how to do this using integration by parts. We can actually do this using this new complex form for sine and cosine. Even though x is real, we can take this circuitous route into the complex numbers and we still come back to a real answer at the end. Let's try it as follows. So combining the exponentials and simplifying, then I can integrate. assuming that the usual rule for the exponential integral goes through, then I can tidy this up by collecting factors of 1 plus I, 1 minus I on the denominator. And of course that's a real number because it's a number times its conjugate on the denominator. The numerator then becomes, and now because the denominator just factors into 2, we end up being able to simplify this whole thing, which is exactly what we would get doing integration by parts.